Today we are building a smart parking management system. Not only will we count cars entering and exiting, but we'll also read license plates and send real-time notifications to your phone. The best part, you can do all that with minimum coding using Roboflow workflows, an open source ecosystem for building complex image and video processing pipelines. We've been hard at work with workflows for a few months now, and I'm excited to show you what's possible, so let's get started. We'll start by logging into Roboflow, then from the panel on the left, we'll select Workflows and click Create a Workflow button. Depending on your needs, you can run workflows in a few different ways: hosted API, dedicated deployment, and local inference server. The default option is hosted API. It works out of the box and use pay-as-you-go pricing, as you share the environment with other users and only pay for the time you used. However, it has some drawbacks. It's limited to CPU-only operation, can't process videos, and does not support custom Python blocks, which we'll need for today's demo. The second option is dedicated deployment. We pretty much spin up your own machine on our infrastructure. You get to use GPU, you can process videos and run custom Python blocks, but it's a lot more expensive as you pay for the whole time that machine is online. And the third option is you spin up your own local inference server and only connect it to workflows. This way you will get most of the benefits of dedicated deployment, but at almost no cost other than the power to run your own machine, and that's the option that I will show you today. Setting up a local inference server is actually quite simple. All you need is a machine with Python and Docker configured. I'll start by creating a separate Python virtual environment for this demo. As I always say, it's a good practice to run all of your projects in separate Python virtual environments. This prevents dependency conflicts and keep your projects organized. Once I have the virtual environment up and running, I'll run pip install inference CLI. This is a lightweight Python package that allows you to start and stop the server with simple terminal commands. And now that the installation is completed, let me show you that I don't have any Docker images locally. I actually deliberately removed all of them before the recording so I can show you that our next command will pull that image automatically. So let's run inference server start. And as I said, this command will pull the inference server and run it. Depending on your internet connection, this command may take a few minutes to complete, so let's use the magic of Cinema to speed up the process. Once the command is completed, we can run docker ps to confirm that the server is online. And indeed, we have the server up and running. It was started 12 seconds ago and it's available at localhost 9001. Now that our server is up and running, let's connect it with workflows. I'll just click the connect button, and after a few seconds, we should be good to go. You'll know that everything is okay if you see this green checkbox next to running on localhost in top left corner. Before we define the actual workflow, let me change the name and the URL. The name is purely for convenience, just like with Jupyter Notebooks or Google Colabs. You don't want to end up with undefined for underscore final or whatever. I'll give it a descriptive name to keep things organized. However, the unique URL is important. We'll use the whole model-examples/parking-lot-management to identify the workflow when running it locally. I'll press the save, and finally we are ready to add our first block. I'm going for object detection model, and for now I'll use YOLO V8 pre-trained on Coco dataset checkpoint. I'll type in YOLO V8M-640. Don't worry, I explain how I came up with this intuitive model ID in just a second. But to easily examine our model's predictions, we need some visualization. So for now, I'll keep it simple and only add 2 blocks: bounding box visualization and label visualization. This way we'll see bounding boxes around every prediction, along with label with the class name. Lastly, before we run it, let's make sure that label visualization is part of the response. Looks like this, so I'll save the workflow and let's go to Test Workflow tab. Here I can choose whether to run the workflow on a webcam stream or on a video file, but for now I'll stick with simple image inference. Before recording, I extracted a single frame from our input video and I'll drop it here as an image. I'll click Test Workflow, and after a few seconds we see the response. If we take a closer look, we see that it contains the coordinate of bounding boxes, confidence levels, class IDs, class names, and so on, but also label visualization. If we go into Visual tab, we see the predictions are drawn on the image. Now, let's take a step back and let me explain where did that YOLO V8M640 model ID came from. It's one of pre-trained Coco checkpoints available in workflows. We support over 30 models pre-trained on Coco dataset, ranging from YOLO V5 up to, I believe, YOLO 11. You can find the full list of supported checkpoints in Microsoft Coco project on Roboflow Universe. The link to the project is in the description below. So, if you would like to experiment with different architecture, different model size, or different input resolution, all you need to do is copy that model ID from Roboflow Universe, paste it into your object detection model block in Workflows, save it, and you should be good to go. To know which cars have entered and exited the parking lot, we need to be able to detect and read license plates. Unfortunately, Coco dataset does not include this class, so we need to swap our current model for one trained on dataset of license plate images. I spent some time looking for a good model on Roboflow Universe and found this one, trained on nearly 9,000 images. It looks like it should work for us, but to be sure, let's run inference on frame from our input video. I'll just drag and drop it into the browser, and after a few seconds, we should see the result. Both license plates were detected. This looks quite promising, so let's copy the model ID and head back to Workflows editor. Let's click on Model ID and swap our current model for the one copied from Roboflow Universe. But before we run our demo, let's make few updates to our visualization. Workflows visualization blocks are based on supervision annotators, allowing for a wide range of customization. Let's change a color of our box and labels to bright orange and label text to black. We'll save the changes and run our workflow once again. I'll click Test Workflow, and just like last time, I see the response. If we go into the Visual tab, I see that, as expected, our license plates were detected. Now, let's experiment with reading the license plates. We can do it in many different ways, but I decided to use the output of our license plate detection model to crop out portions of input video frame containing the plates, and then using OpenAI's GPT-4o vision model to read them. All the blocks we need are already part of workflows, so we don't need to write any custom code here. I'll start by adding a dynamic crop block to my workflow, and then I'll insert an OpenAI block after it. This allows me to define a prompt that I want to send with each of the crops. I'll simply ask the model to read the text from the image. And of course, I'll also need an OpenAI API key, which you can generate after logging into your OpenAI account. It's time to test the idea, so let's save the workflow and let's make sure that the crops and OpenAI output are part of the response. Now we can run the workflow once again. Notice that when I click test workflow, the execution takes a little longer because I'm not only running the license plate detection model, but also calling OpenAI API to ask about the text on each of the crops. Scrolling down the result, I see that both plates were cropped as expected, but OpenAI GPT-4o Vision read the text correctly for the first plate, but not for the second. I identified two problems that might cause the model to underperform. First, we cropped already annotated image, and the bright orange lines we drew might confuse the model or obscure parts of the text. Second, we cropped the image very tightly around the license plates, putting the text close to the edge, potentially making it harder to read. Let's go back to editor and try to fix this. First, I'll click on dynamic crop block and set image to crop to input image. Then, before dynamic crop, I'll add a detection offset block, which will pad my detections with extra space. Let's say 20 pixels vertically and horizontally. Let's just make sure that dynamic crop now uses our padded detections. It does. And finally, we can save and run our workflows again. I'll click Test Workflow, scroll down to see the results obtained from OpenAI API, and this time everything works. Okay, it looks like we can use a similar setup to process the entire video. However, due to the time required to call the OpenAI API and the cost of such requests, we need to slightly rebuild the pipeline. Instead of calling the OpenAI API for every frame of the video, let's try to do it once for every car we see. To do this, we'll have to track the cars appearing in the parking lot. Let's temporarily remove the OpenAI, dynamic crop, and detection offset blocks. Instead, let's add a detection tracker directly after object detection model block. Inside additional properties, I'll set the minimum consecutive frames to 3. This means that the new object will have to be visible on at least 3 frames before it's assigned a tracker ID. This will make our workflow more robust to potential false positives. Finally, I'll add a trace visualization to draw the path traveled by tracked objects. As before, I want it to be drawn in bright orange. I'll also set the length and the thickness of the drawn trace. And now it's time to test our workflow on full video for the first time. Support for video processing is still limited in Workflows UI, but you can run it locally using inference package. To do this, let's go back to our local Python environment and install the inference package. The installation takes only a few seconds. And once it's completed, I create a new Python file called app.py and open it in my IDE. Now we'll write a simple script that will run our selected workflow locally and display its output on the screen. We'll start with from inference, import inference pipeline. Those of you who regularly watch our videos might remember that we already used this utility in our time and zone video. Next, we'll create an instance of our inference pipeline using init with workflow method. It takes several parameters. The first one is video reference. In our case, it's the path to local video file, but it can also be a webcam or RTSP stream. Next, we need to provide information on which workflow we want to run. We specified using the parameters included in workflow URL. The part before the slash is workspace name. The part after the slash is workflow ID. I'll copy these values from the Workflows UI and paste them into my script. Optionally, I can also define a callback that will be executed for each frame. I'll call it custom sync, and above I'll create custom sync function, which according to Workflows API must accept predictions and video frame arguments. For now, let's use it to display the processed video on the screen. I'll import OpenCV. Then from predictions, which is Python dictionary, I'll extract the value stored under traced visualization key. I can do this because when defining the workflow, I made sure that it will be part of the response. Now using the standard OpenCV, I'll display the frame on the screen and add wait key call, allowing me to interrupt processing. At the end, I'll call pipeline start and pipeline join. Inference pipeline uses separate threads for video decoding, performing the inference and dispatching the result. Hence, the additional start and join methods, they allow you to start the processing and gracefully terminate it. Before we run the workflow locally, we need to take care of one more thing. The workflow is tied to your Roboflow account, so you need Roboflow API key to run it locally. You can find your Roboflow API key by logging into your account, clicking Settings in the left panel, and then navigating to API keys. Here you can copy your private API key, then go back to terminal and export it as environment variable. Now you can just run the script by calling python appy. And here's the result we obtained. We can see that the license plates are being detected and tracked, and their movement paths are drawn on the output video. So far so good, but how will we know which car is entering and which is exiting the parking lot? Well, to do this, we'll use line zone. Let's go back to the workflow editor and I'll show you how to add it to our video processing pipeline. We need to add two blocks, line counter and line counter visualization. The first will be responsible for counting objects crossing the line. I define the starting point of the line as 1000 by 100 and the end point as 1000 by 1080. These values are x and y coordinates expressed in pixels, creating a vertical line roughly in the middle of frame's width. Line counter visualization will be responsible for drawing the line and displaying the values of in and out counters. Almost 2 years ago, I created a video on this channel where I showed you how to program the entire line counting mechanism from scratch in Python. And today, it only takes 2 clicks to add the line counter to your workflow. It's kind of crazy how far we come. After adding the new blocks, we'll save the workflow and make sure line counter visualization is part of workflow result. Because visualizations in workflows are applied sequentially, in our workflow, the line counter visualization comes after the trace visualization block. We need to go back to our app.py script for a moment, and instead of extracting the value under trace visualization key from predictions, extract the value under line counter visualization. Let's take a look at the result, and as before, the license plates are detected and tracked, and their movement paths are drawn on video frames. But now, depending on whether the vehicle is entering or exiting the parking lot, the in or out counter is incremented. You can also see how strategically the line's position was chosen, allowing for the correct counting of moving cars even when they are moving in opposite directions simultaneously. This is okay for the purpose of the demo, but I think that in real-world system, the movement to and from the parking lot would be observed by 2 separate cameras to avoid the risk of exiting vehicle being obscured by the entering one. Besides counting the objects crossing the line counter returns a list of objects that crossed in or out in a given frame. Now we can use this mechanism to read the license plate only once when the vehicle enters or exits the parking lot. To do this, we'll use conditional if block, which executes the following blocks only if the condition assigned to it is met. Let's say we want to execute the following blocks only if the number of detections that have crossed the line in the in direction is greater or equal to 1. Let's remove the line counter visualization from here. Instead, add the detection offset block we already know, making sure it uses detections in as an argument and setting the vertical and horizontal padding to 20. Next, let's add dynamic crop, making sure it uses input image and the padded detections in. And at the end, let's add OpenAI block asking it to read the text from each crop. We of course need to include the OpenAI key as well. Finally, let's add the OpenAI output to the workflow result, calling it OpenAI detections in. Before running the app UI script, let's jump into our text editor for a moment and modify our custom sync function. Instead of displaying the visualization, let's print out the value of OpenAI detections in the terminal. We'll start by commenting out all the code in custom sync function. Now let's extract the value associated with the OpenAI detections in key from predictions and assign it to a variable. To avoid spamming the print statements for every frame, we'll check when the value is non-empty and only then print it in the terminal. When we run the script, we see that every time a car crosses the inline, a single element list containing its license plate number is printed in the terminal. To better visualize the result, I overlaid the video with the visualization from the previous step. However, nothing happens yet when the vehicle moves in the out direction. Let's make all the necessary changes to capture that as well. This part might seem a bit repetitive as we already did all those steps for detections moving in the in direction, so let's watch this clip on a triple speed and allow me to explain what's happening in the meantime. We're essentially adding a second branch with conditional if, detection offset, dynamic crop, and OpenAI block, conditioning its execution on the presence of detections in the out direction. Before we run the script again, let's make sure that the license plate numbers of vehicles moving in the other direction will also be visible in the terminal. Let's extract the value associated with new OpenAI detections out key and assign it to new variable. As before, let's check if the value is non-empty and if so, print it in the terminal. When we run our updated workflow, the terminal will display the license plate numbers for cars moving in both in and out directions. Now that we are sure that everything is working as expected, let's figure out a way to send the extracted license plate numbers as phone notifications. To send a notification to my phone, I decided to use a Telegram bot. It's super easy to set up and only requires a simple HTTP request to send the message. To create our Telegram bot, I'll first need to install the Telegram app on my phone and find bot father. This special bot helps us create new bots. The bot father communicates through commands that starts with /. We'll use the /newbot command to create our bot and give it a name like parking lot management demo bot. Next, we'll choose a username for our bot. Let's use the same name but in camel case. This username is how other users will find our bot on Telegram. Once we created the bot father will provide us with unique token. This token acts like a password, allowing us to send messages through our bot. With the bot set up, we can search for it on Telegram and start a chat. Each chat has a unique chat ID that we will need later to send messages to the correct conversation. We can get this chat ID using the Telegram API. Workflows provide a number of connectors out of the box, such as email, but Telegram is not yet supported. However, we can create a custom Python block to encapsulate any Python code we want and extend Workflow's capabilities. In our case, we'll create Telegram bot connector block. Let's click the plus button to add custom Python block to our workflow. First, we need to define the block name and description. I'll call it Telegram message, and it will send messages via Telegram bot. This block will take the output of OpenAI block, which contains the license plate information as an input. Let's call this argument message, and its type will be language model output. I will return true if the message is sent successfully and false otherwise. Within the block, we'll use request library to make a simple HTTP call to the Telegram API, and this will require two pieces of information. token, the unique identifier provided by Telegram bot Father a few minutes ago, and chat ID, the string that uniquely identifies our conversation with the bot. Going through Telegram API documentation, I found the endpoint and the payload structure we should use to send the new message. Let's start with defining the URL. As for the payload, JSON will store chat ID and text message we want to send. To ensure our block is robust, we'll wrap the HTTP post call in try except block, returning false if any error occur. In the try section, we call requests.post and pass URL and payload as arguments, returning status true if no exception happens. Once the block is saved, we can add it to our workflow. We'll place it at the end of both in and out branches so notification is sent whenever license plate is read. Finally, it's time to take a look at the result. Here's a recording showing my monitor screen displaying the visualization and my phone receiving real-time notifications with license plate numbers. Of course, I might be biased, but I think the result looks pretty cool. Before we wrap it up, let's talk about the challenges I encountered and potential solutions. Right now, we are using one camera to monitor both entrances and exits. This could lead to a problem if a car gets hidden from a view just as it's leaving, causing our system to miss it. Ideally, we'd like to use two cameras, one for entrances and one for exits, to get a clearer view. Secondly, the further I got into this project, the more I regretted the original decision to use OpenAI API to read the license plate numbers. Of course, the model is expensive to operate in the long run, and every API call introduces unwanted latency, but believe it or not, it's actually not the biggest problem. Take a look at this. As we all know, OpenAI censors model responses, and from time to time it simply refuses to read the license plate numbers. The obvious solution to this problem would be to replace OpenAI API with local open source model capable of license plate OCR, like Florence 2. A while back, I showed you this model in action, and I think it should be able to handle this task with no problem. Most importantly, Workflows already has Florence 2 block, so it wouldn't be too much work to replace OpenAI's model. And once again, you can see the clear advantage of local open source models over foundational models behind the API. That's all for today. We tackled license plate detection, object tracking, and even integrated Telegram bot for real-time notification, and all that with minimum coding. It's really exciting to see how workflows can empower people to build complex computer vision projects even without tons of experience in the field. If you enjoyed the video, make sure to like and subscribe, and stay tuned for more computer vision content coming to this channel soon. My name is Peter, and I see you next time. Bye.